What would you think? Monodentate, bidentate? You know, it's got 4 lone pairs. So monodentate, bidentate, tridentate, tetradentate? Monodentate. Why? Why can't these other lone pairs also bind? Make it.
It can't stretch out to a different location.
It can't stretch out to a different location. When you look at this ion, what do you visualize as far as, you know, where we can't? Can we pinpoint where the lone pairs or where the electrons are located? No, but what we do have is we have what? We can't pinpoint, but we do have what? A probability, and that probability is given by a equation, yes, but visually it's given by a. What do we call the probability? You know, that the shapes of those probabilities. Electron clouds or orbitals. Yeah. And so we do have orbitals showing us the probability. You know, usually with the orbitals, what does the orbital typically represent? You know, if you draw a line, represents the 100% boundary, 95% boundary, 85% boundary, 95% boundary. And so when you look at this, what do you see? What orbitals do you see for these electrons? sp3, right. And so when we're thinking about sp3, you know, if we have, let's say, 1 lone pair here coming at the metal, where are the other 3 lone pairs located? In the tetrahedral configuration. So they're on the opposite end, right? We're going to have something like this where we got the 3 lone pairs, but they're pointed in the wrong direction. And so we've got this orbital coming to attack the metal here, right? There's no way these can also overlap with the central metal geometrically. And so we can kind of figure out, you know, there are some that are tricky to figure out. You know, is it monodentate or is it bidentate? Let's look at this one. Carbon dioxide. You know, these are base sites, right? Lone pair. Negative charge density, these are delta minus. Would this be monodentate or bidentate, do you think? Again, this would have to be a monodentate because this would be a lone pair in what type of orbital? sp2. So if that comes to attack, then these other orbitals are pointed off in different directions. And so examples of monodentate. And so let's take a look at some variety of Lewis bases here, and then just see if the basic atoms, you know, how many atoms will coordinate with metal. So there's a table of ligands or table of bases in your book. These are the common ones. Pull it up here. 24. Oh, we talked about these, right? Did we? I don't remember. Aqua, amine, carbonyl, nitrosyl. And so when we look at something like carbonyl, you know, we should be able to tell, easily this is going to be a monodentate rather than a bidentate because it looks like it has the potential to be a bidentate ligand, doesn't it? I mean, if this pair binds, why not this pair here? What do you think? No, because if this pair binds, what's the hybridization on this carbon? SP, this is 180. What's the hybridization on oxygen? This is 180. So these are 180 apart from each other. So if this one attacks the metal, the other pair is on the opposite end. There's no way this could be a bidentate ligand. Now when I say this attacks, you know, it attacks and does what? Does an orbital overlap with the metal orbitals? Or does an LCAO with the metal orbitals? Linear combination of atomic orbitals. All right, so here, these are the neutrals that we change the name, and then here, all the other neutrals, we don't change the name. So something like methylamine, the nitrogen here has a lone pair, it's not shown. This would be a monodentate, bidentate. Just looking at it, what would you say? Monodentate, there's only one donor. Are there any lone pairs on the carbon or the hydrogens? No. Puridine's the same thing, except this has a ring structure, but it has a lone pair there. It can bind. And so these are examples of what we call the amines. The amines with one M represents what again? A group of compounds that have an ammonia-like structure. In other words,
So it's not really.
it's not really, this is not ammonia, but like pyridine is an amine. Right? What makes an amine? What makes an amine is the nitrogen is either bonded to hydrogen or carbon. Because carbon and hydrogen have very similar electronegativity. And therefore, if you bond a carbon or hydrogen, it's not really going to change the electronic environment around nitrogen that much, right? Since it has similar electronegativity. How about this one? Is this an example of an amine? It kind of looks like I don't have a decent pen. Nitrogen trifluoride.
No.
Is that an example of an amine?
No.
Why not?
Doesn't have to be bad.
It looks kind of like ammonia. Why doesn't that qualify as an amine? That, you know, that's simple. That's simplistic. That's what I said, but you missed the second part of what I said.
It's an electric environment.
It's the electronic environment around nitrogen. An amine is a base. A base is going to be a lone pair and what? Negative charge density. So, you know, something I didn't do is this. When we do, you know, what charge density? What are the formal charges here? What are the formal charges here? Zero. What are the formal charges here? So what am I talking about charge density for? They're all zero, aren't they? Well, when we look at the oxidation states, you can easily tell. Now, the oxidation states, I didn't really go through the rules of how I do oxidation states based on structure. But oxidation states, what's the assumption you make when you count electrons using oxidation state? That's 100% ionic. And so let's just do oxidation states here. When we do oxidation states, if it's 100% ionic, the bond, who gets the electrons, fluorine or nitrogen? Fluorine. So fluorine takes all the electrons. Fluorine takes all the electrons, we assume the bonding is 100% ionic, and then count the electrons. So nitrogen only ends up with 2 electrons in the structure. It's supposed to have 5 electrons. That means it's a deficit of electrons of plus 3. It's going to have a net plus 3 charge because it has more protons than electrons, right? an imbalance of protons and electrons. Whereas fluorine, yeah, fluorine's going to end up with 8, and so it gains 1, so it's -1. Each of the fluorines are the same at -1, right? Now, here we assume the bonding is 100% ionic, but nitrogen versus hydrogen, who's more electronegative? Nitrogen. Nitrogen wins all the electrons. So nitrogen ends up as -3, hydrogen ends up as +1, all of them. So we can see that these two nitrogens should behave dramatically different. Would you consider this nitrogen very basic? No. No, I would not consider this nitrogen very basic. Why? Because it's got a lot of positive charge density. We could do the same thing with delta pluses and delta minuses. Fluorine's more electronegative, that gets delta minus. Nitrogen's less electronegative, gets delta plus, right? Tells us the same thing, but using oxidation state sometimes is quick and easy to do. Here, and so this is considered a mean. What if we put carbon here? If there's a carbon here, who wins, nitrogen or carbon? Nitrogen. So do you see putting in carbon here doesn't change anything? And so that should be an amine. So we could put a methyl group here, an alkyl group here, whatever we want, propyl group. It's not going to change it. And so this is not an amine, this is amine. So this is why I say carbon and hydrogen, since they're very similar. And so this, nitrogen's bonded to carbons, nitrogen's bonded to hydrogens and carbons. These are all amines. These are organic. These are all weak Bronsted bases. And it turns out, as far as Lewis bases go, they're pretty strong. These are pretty strong Lewis bases. You know, nitrogen is really good at being a donor. But, you know, it's kind of funny because if you have something like nitrosyl is a structure for nitrosyl, or nitrogen monoxide. So if we look at the Lewis structure for nitrogen monoxide, what does it look like? Does it look like something like this? Like carbon monoxide? Remember carbon monoxide? Yes? No, right now I have too many electrons. Nitrogen has 5 electrons, oxygen has 6, so that's a total of 11 electrons. So 11 electrons. Did I already cover this yesterday? No. Okay, we had a power outage, so I got out of sync completely in the 2 classes. So I covered totally different stuff in the afternoon. Well, anyway, here, because I didn't have slides to show. So we had 11. We want to complete the octet to oxygen and try to complete the octet to nitrogen. So this is what we end up with. All right, 2, 4, 6, 8, 10, 11 electrons. Nitrogen is going to have less than an octet, or oxygen is going to have less than an octet. Who should have less than an octet? Nitrogen, because nitrogen is electronegative. Figure out. Well, anyway, going to here, which one's going to be the donor? Is nitrogen going to be the donor or oxygen going to be the donor? Nitrogen. Nitrogen, why?
Free radical.
Well, nitrogen is free radical. Free radicals have a single electron here, but if it's a donor, is that going to cure? You know, if it's a donor, it has to bond a lone pair. So does that fix the free radical? No, it doesn't, so it stays a free radical. So free radical is not the reason because it's still a free radical. And so it's tricky because you would think, well, which one should be more negative? The oxygen. So maybe the oxygen should be a better donor. But, you know, when I'm talking about that, that's the first thing we look at. And there are different levels that we analyze things. You know, we try to analyze things simplistically, but there could be other factors. And one of the other factors is this whole idea. Remember about the hard, soft? Does anybody remember that? What was all that about, hard, soft?
Like bonding is preferable.
Like bonding is profitable, right? Hard, hard, soft, soft. And so that changes things as to what is a better donor. And so sometimes you expect, well, oxygen should be a better donor because it's got more negative charge and this is more positive charge density, right? doesn't even have an octet because of the polarity. We look at the oxidation states as the saying the same thing. This is going to be a +2 oxidation state. This is -2 oxidation state. And so, but we can say all that and say negative charge, and that's good. But when it comes down to it, it depends on the LCAO. You know, how good of a linear combination of atomic orbitals you end up with, right? That's going to dictate which one's a better donor. And for these metals, it typically is, metals are typically hard ions. And so, well, for metals, it can get tricky. And so what we do is we just kind of learn an order. You know, this is what's observed, and then sometimes we don't know which one's going to bond. And so, for example, the classic example is, it might be this, you know, the nitrogen or the oxygen. It turns out nitrogen typically is a better donor than oxygen, even though you might expect oxygen to be a better donor. And that just has to do with how the bonding is. Well, sometimes, you know, there isn't a huge difference. And that would be for something like this. You know, nitrite, NO2. And so when we look at nitrite, let's do the Lewis structure for nitrite. You know, when I look at the Lewis structure for nitrite, I would say this oxygen should be the best donor. This oxygen has a full negative charge, and it's got a lone pair. And so I would think this would be the best donor atom. And in fact, it can bond that way. We call it, when it bonds to the oxygen, we call it nitrito -O-. That's to indicate it's bonding to the oxygen. But, you know, because of the orbitals and you know, making these molecular orbitals is more complex than just simply looking at negative charge density, you know, nitrogen can also be the donor, the key donor. And typically it's the nitrogen that bonds in nitrito. And so if the nitrogen donates here, then we call it nitrito N. Nitrito N is so common that people just shorten and just call it nitro. And so when you see nitro, nitro is just NO2 bonded with the nitrogen. Good. Could this be a bidentate ligand? Do you think we could have both these oxygens bind? No. What would the problem with having both these oxygens bind be?
One is sp3, the other one is sp2.
But this nitrogen's sp2, so this is angled like this, so both can come in. You know, this is trigonal, oh, this is bent, you know. Geometry is bent. This is trigonal planar electron geometry. And so both of these could potentially bind because they're in the right position, but what?
The molecular orbitals are.
If this were linear, for sure, no. But this is not linear, this is bent. And so potentially, yes. But the angle, it would form what membered ring? 1, 2, 3, 4. It would form a 4-membered ring, right? Are 4-membered rings stable? No. And so this would be that sulfato. You know, sulfato, is that a monodentate or bidentate, you know? Sulfate. So if we look at sulfate, you know, sulfate's tetrahedral like this. Could it be bidentate? You wouldn't expect it to be bidentate because 4-membered ring. You know, although it's a big one, it's a big ligand. And so I'd expect all these to be monodentate. You know what thiosulfate is? Thiosulfate is you just replace one of the oxygens with a sulfur. That's thiosulfate. Thiocyanate can do the same thing. Thiocyanate can bond with either the S or the N. And depending, sulfur is a softer atom, nitrogen is a harder atom. So it depends on what it goes to.
What does it mean to be hard or soft?
Hard or soft is just size. You know, polarizable. Things that are very polarizable are soft. Things that aren't very polarizable are hard. And so big electron clouds are soft or hard? Soft. Small, tight electron clouds are hard, right? Hydroxo. You know, what should be a better donor? A hydroxo or an aqua? What do you think is going to be a better Lewis base or ligand? Why? Hydroxo, you're right. Because it has a full negative charge versus a partial negative charge. You know, the formal charge on this is 0. All right. Did I talk about what we do with the names already? You know, for the anions?
Yeah.
Like fluoride gets changed to fluoro. Just change the ending to O. That's pretty much it. Unless it's neutral. Did I talk about oxalate yesterday? No? This is oxalate, C2O42-. As a ligand, we call it oxalato. This is the abbreviation we can use in the formula, OX. When you look at oxalate, what do you think? Is it a monodentate, bidentate, tridentate, or tetradentate? This has got to be bidentate. And if you had to choose, you know, which oxygens would you choose to be the donor? The two on the bottom with the negative charge. It turns out because of resonance and the resonance hybrid, all 4 oxygens are the same. You know what the charge on all 4 oxygens is in the resonance hybrid? Negative. Negative what?
Well, there are 2
Negative half, right. And so each of these are all the same at negative 1/2, and the bond order is all the same at 1.5. Does that all sound familiar? And so this is an example of bidentate, and then we looked at this one yesterday. This is a hexadentate. But if you look at how many donors we have, you know, can both these oxygens here donate? No, only one can, because if both did, you'd form a 4-membered ring. Right. Okay, so we can figure out what the donor atoms are. So this is a little bit about the structure. And let's take a look at some of the homework problems. Write the formula and name of a complex having chromium-3 as the central ion, 2 ammonias, and 4 chlorides as ligands. So let's write the formula out. When we write a formula, what comes first? Well, put a square bracket. Do we put the ligands first or the metal? Metal always goes first. So we put the chromium here. followed by the ligands. Now, do we put the anion ligands or the neutral ligands? Anion ligands first. And so we have 4 chlorides. This is regardless of alphabetical order. And then the neutrals, we have 2 ammonias. We need parentheses around these to show this. And here. What's the total charge on this? Yeah, +3, -4, -1. There we go. How would we name it? Now, when we name it, do we name the metal first or the ligands first? We name the ligands first. Do we name the anion ligands first or the neutral ligands first? Doesn't matter. We name the alphabetically, right? And so this would be called. Okay, with 1M or 2M? Okay. Space or no space? And then what? Tetra, chloro, chromium. There's supposed to be no space here. Chromium. Is there a space between the chromium and the 3?
It's chromate.
Oh, yeah, you know, you're right. It's chromate because of the negative charge. Whenever the complex carries a negative charge, we have to change it to the 8 ending. Is this chromate 1? No, it's chromate 3 because the metal is 3 plus and the chlorides are -1. And so this would be an ion. There. A complex ion of iron 3 having a coordination number of 6 and cyanide as the ligands. So let's go ahead and do that. Did you guys already do these?
No.
Yeah,
I did.
you did. Maybe we should do,
Is it chromate or chromium?
It's chromate. It's chromate because it's a negatively charged. It would be chromium if it had a positive or neutral charge. Let's look at B because B is a common one. Cyanide, is it monodentate or bidentate?
Mono.
It's going to be monodentate. And so if we have a coordination of 6, we need 6 cyanides to do that. What's the total charge on this complex?
3 minus.
3 minus. And so this would be what?
Hexes, cyano.
Hexacyano. Iron?
Very.
Yeah, ferrate. If this were a positive or neutral, we would just call it iron. Since it's negative, we have to use this funny one. Ferrate 3. Ion. Hexacyanoferrate 3 ion. So, a coordination compound comprising 2 types of complex ions. One complex of chromium 3 with ethylene diamine having coordination number 6. So we have chromium 3 with ethylene diamine having a coordination number 6. So let's go ahead and do that. If we put a chromium here, we need a coordination number of 6. That means we have to have 6 bonds to the chromium. How many ethylene diamines? Could we put 6 ethylene diamines?
1.
No. 1? Yeah, we could put 1 ethylene diamine. Yeah, 1, 2, 3. Right, like that. This would be an octahedral structure. This has a coordination number of 6, but it's only coordinated to how many? 3. 3 ligands it's coordinated to. The formula for this is Cr En 3 charge 3 plus. Ethylene diamines are neutral. And the name for this? Actually, we named this already. Tris ethylene diamine chromium 3. Good. Did you finish all these, Arthur?
Yeah.
You did? All right. I don't want to repeat these for you. Let's look at some more. Some ones that you haven't seen before. How would you name this ligand? A. B. CH3 is called methyl, and this is what kind of organic compound? Amine, methylamine. ONO minus. Nitrito hyphen O hyphen. This one is cyanate, but with a sulfur, so it's called thiocyanate, and we don't know if it's S or N. Maybe it's.
Doesn't the nitrogen come first if it's sulfur first if it's sulfur?
Okay.
But both of those.
Okay, that's fine. Hydroxo is what?
Hydroxide. OH.
Did I assign these?
Yeah, I guess.
Oh, all right. Forget that. Did I assign these?
No. Wait, I think you went up to 7. You did 7A and 7C.
All right. 7A, 7C, assigned those. 1 up to 10. Let's do some more. I didn't assign these, did I?
No.
All right, what's the coordination number of chromium?
6.
6. 5 amines, 1 hydroxo. And what's the charge on chromium? +3. What's the name of this?
Hexane. Oh yeah,
Pentamine, hydroxo, chromium 3, Roman numeral. No spaces. How about this? What's the name of this? Tetra. Tetra, is that tetra? Tetra is 4. This has got to be triamine, aqua, dichloro, chromium 3. This one is called what? Dichloro or bisethylene? Which one comes first? Bisethylene because of B or E? Bis doesn't factor in. It's E for ethylene diamine or C for chloro. So it's going to be tetrachloro, ethylene diamine, not chromium, chromate because of the negative charge. Chromate 3. This one we already did. Okay, this is an example of a complex compound where the cation of this is a complex and the anion of this is complex. So we name the cation complex first, followed by the anion complex. And we don't indicate the number. For example, if we had 2 cations for every anion, we wouldn't say di this cation. And we just, we can figure it out based on the charge. And so this is what? The cation is called tris, ethylene diamine, cobalt. Now, is that cobalt 2 or cobalt 3?
It depends on the anion.
Yeah, so let's see if we can figure it out from the anion. This would be trioxalato, chromate 3. And so this has got to be cobalt +3. If this were 2, then this would have to be +4. Does cobalt +4, is that a stable oxidation state of cobalt? No. Okay, here you can see an oxalato. This is the shorthand way of representing oxalato. Like this, just like ethylene diamine. Or we could write it out. All right, so that's some practice with nomenclature, coordination number, oxidation state. We're going to jump back to chapter 15 here. take a look at these. Any questions from chapter 24? So, chapter 24 quiz, will be next week, Tuesday. And so just complete your chapter 24 homework and turn that in the day of the quiz. Your homework you could either do on loose leaf paper or, I don't know why this keeps, or you can do it in a notebook. If you do it in a notebook, normally when I check out the homework, I check it off. It's going to be a short quiz, so I might not have enough time to check it off rapidly, but I try to check off the homework and hand it back to you on the same day. And so if you want to keep it in like a sewn-bound notebook or a spiral-bound, and you don't want to tear out the pages, just turn in the whole notebook. I'll give you back your whole notebook. That way, it's nice to have a homework notebook because that way you know where your homework is. It's always in one place, not scattered about. All right, in chapter 15, we're talking about chemical equilibrium. And I talked about this a little bit before, and what we have here is we have some very tricky stoichiometry. The tricky stoichiometry is the reaction doesn't go to completion. Like you mix the reactants together, and you start forming the product, but then it stops. It stops. It doesn't go all the way to completion. And then that's the end of the reaction. No further net reaction takes place. This is what we call dynamic equilibrium. And what's happening there is this. You can have both the forward reaction and the reverse reaction occur. And so as the forward reaction occurs, you have collisions between the reactants. Those collisions generate the forward reaction. But as you're making product over here, you still have, typically the reactants, in thermodynamics, the reactants and the products are at the same temperature or different temperatures? At the same temperature. So even in the products, you're going to have collisions between the products happening, right? And as you have the collisions between the products, then the reverse reaction can take place. And so can you stop collisions? What's one way you can stop collisions from happening? Cool it down to 0 Kelvin, and then you aren't going to have any collisions. But anything above 0 Kelvin, then you could have some collisions occur, right? And so what happens is there's a balance, the reverse reaction. Sometimes, the reverse reaction is so unfavorable, you have all these collisions but nothing happens, right? Sometimes the reverse reaction is not so unfavorable, so you got a collision and it goes back. This is like, remember when we were talking about CO2 and water? CO2 and water, they collide, they make that funny thing. That funny thing can break apart back into CO2 and water, or you could have the intramolecular proton transfer and get to carbonic acid. So that's an example of a reversible reaction. It could go either way, right? And so typically what happens in these stoichiometry problems is, you start building up the concentration of product. As you build up the concentration of the product, then the frequency of collisions increases and you get more reverse reaction. And if the reverse reaction has any little bit of favorability to it, then you aren't going to have 100% forward reaction occur. Because you're going to reach a point where we reach a point called a dynamic equilibrium. And that point of dynamic equilibrium is when the rate of forward reaction, going this way, is equal to the rate of reverse reaction, and so there's no further net change. And so this is our state of equilibrium. We aren't going to form any more product, and we aren't going to react any more reactants. We've reached the end of reaction. Now, that's equilibrium. Equilibrium means no change, but dynamic means change. And so in a dynamic equilibrium, what's the dynamic part? Dynamic equilibrium. Dynamic part is that the collisions, can you stop the collisions from occurring? No. And so the reaction never stops. The forward reaction, the reverse, it's just that they're balanced now. And there's no further net change. So nitrogen and oxygen is a very stable mixture, right? Quite a stable mixture. And so you don't expect much reaction. This forward reaction is very unfavorable. But under the right conditions, like a lightning strike here, under high temperatures, And also under high pressures, you can form oxides of nitrogen, like NO. NO is not that stable, so it'll decompose. But what happens is some of this nitrogen-oxygen reacts to form a little bit of NO, and this isn't going to go 100% forward when there's lightning strikes. So a little bit of NO forms, and we reach this state of dynamic equilibrium. You can smell the NO. NO is also a component of smog. We've seen dynamic equilibria before. Where have we seen dynamic equilibria? Dynamic equilibria, can you give me some other examples of dynamic equilibria? Not necessarily in chemical reactions, but you've seen this in physical processes. Like if you try to dissolve sugar in water, eventually you put in so much sugar, let's say, if you try to dissolve 15 sugar cubes in your cup of coffee, will it all dissolve? Likely not. You're going to saturate the coffee with sugar. Once it's saturated, you aren't going to be able to dissolve any more sugar. And so that's an example of a dynamic equilibrium in a physical process, dissolution. But does dissolving stop? No, dissolving doesn't stop. You're still breaking off chunks of the crystal. The only thing is, breaking off the chunks of crystal, the dissolution is exactly equal to the crystallization rate. The sugar molecules coming back and sticking. And so the crystals are constantly dissolving and crystallizing at the same time, and we've reached a state of dynamic equilibrium where there ceases to be a net change, but it's always changing. And so here you can see some saturated solutions. You can read about the examples here in the text. I'm not going to go through all these examples. But what we want to do is we want to figure out, in a saturated solution, it's easy because no matter how many sugar cubes you add, it'll reach a state of saturation and stop. And that state of saturation just depends on temperature. So as long as you have the same temperature, the maximum sweetness of your coffee is going to be the same for everybody, right? And so when we're dealing with something like that, then all we say is it has a solubility. Sugar has a solubility. You can dissolve this many grams per 100 milliliters of coffee. If you have 200 milliliters, it dissolves double that. 300 milliliters, triple that, right? It's easy to predict. So our chemical reaction is the same way. That is, it always goes to the same kind of percentage. And so this reaction always has a 95% completion, or this reaction only 50%, or this reaction only 40% reaction. And so we have some reactions here. Let's skip these examples. And then take a look at this table. So the reaction here is going to be copper 2 plus tin 2 yields copper 1 plus tin 4. What type of reaction is this? Is this a metathesis reaction? How do I know it's not a metathesis reaction? I got ions. Well, in metathesis, the ions don't change, and so in metathesis, copper 2 stays copper 2 on both sides, right? And you're right, there's no driving force, there's no ion combination. This is redox. The oxidation states are changing, we got a redox reaction. Now, does this redox reaction go 100%? That is, if I took 2 moles of copper 2 and 1 mole of tin 2, that's what we call stoichiometric mixture, right? Just the right amounts of copper 2 and tin 2. Then how many moles of copper 1 and how many moles of tin 4 will I form? And so I take 2 moles and 1 mole, I should form 2 moles and 1 mole, right? And is there any limiting reactant in this case? No, it's stoichiometric, so I end up with no more reactants and all product. That's Chem 1A stoichiometry, right? But in Chem 1B, you got these collisions, right? And it's going to drive it forward, but when you start forming these ones, Because what's the oxidizer here? Copper. Tin 2 is the reducer. What's the oxidizer in the reverse direction? Tin 4 and... So you have two competing redox reactions. In the forward direction, you have copper 2 is the oxidizer. In the reverse direction, you have tin 4 is the oxidizer. When we predict which direction the reaction goes based on driving force, we say we go from stronger to weaker. Now, in Chem 1A, this is fine. If we're going from much stronger to much weaker, then the reaction should go close to 100%, if not 100%, right? But what happens when the two competing ones aren't so unequal? What happens when the strengths become somewhat equal? Is one going to dominate over the other if they're about equal strength? No, there's going to be a dynamic equilibrium in which there's going to be some partial reaction. And so in other words, we can think of it as maybe a competition or a fight. In this case, it goes forward, but this is fighting to go backwards, right? And so there's going to be some kind of balance achieved where the reaction is going to stop because it's reached this point where the forward is going as fast as it can and the reverse is going as fast as it can, and it's just balanced out. There's no more change, right? And so our job is to figure out, well, what is that? Is it going to be, well, could it be based on this? This is 90% stronger than this, so that we expect 90% reaction? This is 80% stronger than this, we expect 80% reaction? Or what? And so in science, you know, to answer these types of things, we use the scientific method. And let me talk about the scientific method because I do a little bit different organization of the scientific method than Petrucci and biology. In biology, what's the scientific method? Everybody can tell me this because I don't know, they take biology more seriously than chemistry. So oftentimes I ask, what is the scientific method? I get the biology answer. The biology answer is what? I don't know. Biology method always starts with a hypothesis, doesn't it? The hypothesis?
The testable question.
Well, I guess it depends on who you take. Most of my students take somebody who always starts with a hypothesis.
It's called a testable question.
Okay, that's fine. But what we're going to do is, and this is slightly different again than Petrucci, but it's essentially the same thing. We start off with observations because we don't know. You know, this is just, we want to observe nature, and so we start off with observations. This is how nature behaves. And so let's take three observations here. The first observation is we know this is a two-way competition, right? And so we're going to start off with all reactants. We'll go 0.1 and 0.1. Actually, I don't know why they did 0.1 and 0.1 because there's going to be an LR here. What's the limiting reagent? I might have gone 0.2 and 0.1, but it doesn't matter. They just want 0.1 and 0.1. What's the limiting reagent? The copper. Yeah, we need twice as much copper than tin. Do we have twice as much copper than tin? No. So copper is going to be the limiting reagent, right? Okay, so you mix 0.1 and 0.1 and then just observe what happens. And so they let this react for a very long time. And then finally it stops reacting. When it stops reacting, was all the limiting reagent consumed? No. This means this has stopped reacting and we still have limiting reactant left over, which means this is an example of a equilibrium type reaction where the reverse reaction is significant. All right, now what percentage of the limiting reactant reacted? It looks like 36% reacted. Do you see that? 36% of the limiting reactant. Oh, yeah, you're right. You're right. Sorry, that's a leftover. So if that's how much is left over, then how much was consumed? 64%. Only 64% of the living reactant was reacted. Everybody see that? And so that means, oh, that's my observations. So I might think that, well, all these might be 64% reaction. Doesn't that make sense? 64% reaction, which means that, you know, there's a greater driving force forward than reverse, because we got 64% reaction. So more reaction forward than reverse, right? 64% forward. That's good. Now, we take some more observations. So that means if we start off with product, right? If we start off with product, if I start off with product, I'd probably only expect 34% reaction going backwards because I had 64% reaction going forward. And so let's take a look at the limiting reactant here. What's the limiting reactant? Copper or tin? So I'm starting off with 0 reactants and all product. So again, the limiting reactant is copper because I need twice as much copper than tin. I don't have it. This is the limiting reactant. How much reaction occurred going backwards? 56.7%. 56.7%. Do you see a pattern? Do you see some? Because what we do is we take observations and we look for pattern. The pattern I was hoping was 64% forward, maybe 34% reverse, right? If I had 34% reverse, that would leave 64% forward. And does that make sense? And so I look for a pattern, but that pattern I was expecting, did I observe it? No. Because in the scientific method, we go from observation to patterns or trends. And so, well, maybe I need to take more observations to see the pattern, right? And so let's do it this way. I'm going to start with equal amounts of everything, reactants and product, and then see where balance is, because I was expecting 64% reaction. In the first one, I got 64% reaction. But in the second one, I got, what did I get? I got 56.7% going backwards, which means 56.7% going backwards means it's favored in the reverse because I get more reverse than forward. So it doesn't quite make sense. And so I'll take a third observation. The third observation, I just do it and then just see what happens. When I see what happens, what happened? Well, it looks like the forward is favored here, right? But how much reaction did I have? So I start the reaction with this much, I end up with this much. This is the concentration at equilibrium. So how much? 7.8%. Now if I start off with equal amounts, I only end up with 7.8% reaction. So do you see the pattern? So you think, wow, 3 experiments is not enough. I need to take a lot of observations. If I can take a lot of observations, then maybe the pattern will come out, right? But normally, these patterns can be very tricky. And so what people try to do is they try to graph things, right? When you graph things, you're looking for a mathematical relationship, right? Or straight or something. Or you try to take ratios, or you do stuff like that. And so this is the next step. Well, we're just going to stick with these 3 experiments, and then we're going to try to look for a pattern. So here's graphing these. Trying to look for a pattern. So here the blue and the red are the reactants. Reactants get consumed, the products get formed here. And so they just color code it to see, is there a pattern to this? And so I see a pattern like blue, black, red, green. Do you see a pattern here? Do we see a pattern? No. And how about here? No. And so graphing like this, we don't really see much of a pattern there. But sometimes these patterns are tricky, like I said, so maybe there is a mathematical, pattern. And so let's look to see, is there a mathematical pattern? And so the mathematical patterns is like this. Let's go ahead and take the product concentrations. You could do all different kinds of things. This is all guesswork. And science is often like this because you don't know what the pattern is. You're trying to find the pattern. And so you just guess. And so they could have taken the reactants over the products. But in this case, they probably tried that, nothing happened. In this case, they took the products concentration divided by the reactants. And so in experiment 1, these are the equilibrium, where it ends up. Do you see a pattern here? No, this is kind of random, jumping all over. There's no pattern here, So the ratio of products over reactants doesn't work. And then they think, well, because of the stoichiometry, what if we do 2 times the copper and 2 times this copper? Because stoichiometry, they aren't. Do you see? Is this a consistent pattern, this ratio? No, because look at the numbers. They're random. They're all over the place, right? But if you do this, where you square it, if we square the copper and square the copper here, do you see a pattern? Yes. Do you see? Because the copper had a coefficient of 2. Why square? Because they're just grabbing at straws. Trying to find a pattern. Yeah, this is what you do. You spend a lot of time trying to figure, and then, because this is, if you already knew what the pattern was, then obviously you could save a lot of time, right? But if you're just looking for a pattern, you might not ever find it, And so you're just looking, and so they just tried different things, and when they tried this, they saw the pattern. Now, if you get a pattern like this, then what do you want to do with it? You want to make sure it works, right? And after you try it on a whole bunch of different things, and you make sure it works for a whole bunch of things, then we call it a law. We call it a law. You've seen this, the ideal gas law, right? What do we do with the ideal gas law? We do lots of calculations to figure things out. What can we do with this pattern, this law? This is the law of equilibrium. We can calculate stoichiometry because we know the pattern. And so you just memorize the law. What is the law of equilibrium? Let me show you what the law of equilibrium is. This is the law of equilibrium here. This is a more advanced law. This comes later. This comes from the theory. And so I'm going to just do the simple law of equilibrium here. The simple law of equilibrium is this. K is a constant. It's called the equilibrium constant. And what it says is that the ratio of the products concentrations raised to some power called Y over the over the reacting concentrations raised to some power we'll call Z. is a constant at equilibrium. And so if we have a reaction, then for a given reaction, it doesn't matter what concentrations I start with, I'm always going to get the same final ratio, like the previous one, 1.49, 1.48, 1.48, no matter what you start with. And now, we're going to be drawing this a little bit more specifically. This is going to be the concentration of G raised to the little g power times the concentration of H raised to little h, divided by the concentration of A raised to little a, B raised to little b, This comes from this. When we have a reaction AA, little a, big A, plus BB, plus goes to GG plus HH plus And so the coefficient are the little lowercase, and the substance, the reactant of the product, is the uppercase. And so this is the law of equilibrium. You know what we call this? We call this an empirical equation. What does empirical equation mean? Empirical, the ideal gas law is an example of an empirical equation. What is an empirical equation? The law of equilibrium is an example of an empirical equation. Based on observation. Is this based on theory? Did I get this equation from theoretical analysis of quantum mechanics, Schrodinger equation, Heisenberg uncertainty principle, all that stuff? No. This just came straight from observations, empirical equation. It was the same exact thing as the ideal gas law. Did the ideal gas law, was that derived from theory? No. And so how do we use this? We use this in the same way we use the ideal gas law. We just do stoichiometry calculation. But just like the ideal gas law, you start to wonder, about things. Is this the ultimate goal of science? Is just to come up with these empirical equations called laws? No. What is the ultimate goal of science? Is theory. And so on the way to theory, we go from law to... And so what's the difference between a law and hypothesis?
Hypotheses are tested.
No, this is tested too. A law is tested. Otherwise, we wouldn't call it a law. We'd call it a rule with lots of exceptions. Law's been tested, right? The ideal gas law has been tested. The laws of thermodynamics. The laws of thermodynamics have been tested for over 200 years. People have continue to try to disprove it. They try to develop perpetual motion machines. A lot of people say those are possible. Laws of thermodynamics are wrong, but nobody's been successful in making perpetual motion machines. And so lots of people tried to violate the laws tried to disprove the laws of thermodynamics, but have not been. And so the laws of thermodynamics have been tested and tested and tested, just like the ideal gas law, just like this. And so what's the difference between a hypothesis and a law? No, laws aren't always true. There are exceptions to laws as well. Restrictions. What's the difference? There's a huge difference between a law and this is what I'm getting at, because a lot of people just stop at the law. I know the ideal gas law, PV equals nRT. I just plug in 4 variables, 3 variables, I get 1 out, right? Punch it on my calculator. Does that require any understanding? Chemistry? Can an elementary school kid do it? Yeah. Who's had 0 chemistry? Sure. Anybody can do it. Same thing with this. Can anybody do this with a calculator? Yeah. Square, divide, multiply. Very easy to do, right? And so the difference between a law and a hypothesis is what? No, actually, let me stop here and then let's take a break. One more time. Think.